Hi everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to be talking about today is section 6.2, which deals with graphs of exponential functions. Okay. So to start with, let's remember what an actual exponential function's default format is. So the default format is f of x, or f of t, equals a times b to the x. Now what a tells us is the initial value, and what b tells us is the growth or decay factor. Now what this ends up looking like is this. So if b is greater than 1, then we're looking at a situation of exponential growth. And what's going to be happening is it's going to be going like that. It goes up by a factor, and then the result goes up by that same factor, and then the result goes up by that same factor, and so on forever. So notice what's happening is that it is leveling off on the left, and it is increasing on the right. Now this value right here is the A, and then the bigger the B is, the sharper the increase. So let's say this is a smaller B, and then compare that with a larger B. So same A, let's say, but then so this would be what a larger B would look like. So it has a steeper curve upward in the case of exponential growth. And in particular, if we go with just one unit in time, then what we would end up with is multiplying A by B one time. So this would be A times B, would be the height of that. Similarly, this one would be A times B for that one. Now, if B is less than 1, then the entire situation is literally reversed. And what we end up with is exponential decay. And this one still goes through A. So this is decay. And then here we could have one that shows a steeper drop off. But in both cases, these are just the mirror image of what we saw on the other side. So this was decay. B greater than 1 was a case of growth. So then this is still going to be the A, and now this represents a case of milder growth. This represents a case of more drastic, decay. This represents a case of mild decay. This represents a case of more drastic decay. So this represents B closer to 0. Closer to 1. And this is a B closer to 0. Both cases have some very similar situation. Actually, all all of these different cases have very similar situations. Namely, what they all have are very similar stipulations as far as the domain, the range, and their long-run behavior is just a flip-flop of each other. So for a default exponential function, f of x equals a times b to the x, where a is positive, and for that matter, so is b. That's always necessary on b. We have certain things that are always true. So first off, the y-intercept. The y-intercept is going to be 0, a. The domain is always going to be all real numbers, negative infinity to infinity. All real numbers. We can also say what the range will be. The range will always be all positive numbers. Notice in every one of these cases, we are only ever going to get y values that are greater than 0. So 0 to infinity, so in other words, all positive reals. And then they all also have a horizontal asymptote. And that horizontal asymptote is always going to be at y equals 0, and it's always going to only be one-sided. Now, which side it will be depends on whether we're talking about growth or decay. In the case of growth, it approaches that asymptote as we go to the left, so as x goes to negative infinity. If we're talking about decay, it approaches it as we go to the right, in other words, as we go to positive infinity for x. Now we can use some of this information to do some rough sketching by hand of what graphs of exponential functions would look like. And as an example, let's take something like this. So example, sketch. Sketch the following. On the same set of axes. So here what I mean is, I'll give you a few or a couple exponential functions and we'll sketch them together to compare and contrast what they look like. So in the first case, let's say y equals, let's say that our first one is going to be 2 times 3 to the x, and y equals 2 times 1/3 to the x. Actually, let's throw in a third one on there. And then finally, y equals 2 times, let's say, 1.5 to the x. So we have here our 3 exponential functions, but they all share the same value for a. And in particular, so let's say this one is graph 1, graph 2, and graph 3. So they all share the same value for a, but what they differ in is their values of b. So let's say that this is the a of 2, and now if we were to look at what each of these graphs goes through that exact point, but if we look at what happens one time unit later, or one step to the right, each of these y values gets multiplied by its different growth or decay factor. So this first one, the first one is going to be going up by a factor of 3. And so what that's going to be producing is a value of 6. And then what happens is the next step up will be even more profound, and the next step up will be even more profound from that. Meanwhile, going backwards in time, we are going to have a y value at -1 of this divided by 3. So that's going to be 2/3, which is going to be like right here. So this is going to be the graph for 1. So it's going through the point 0,2, and it's rising very rapidly. On the other hand, this graph is going through the point 0,2, but it is going in reverse. It's getting cut down by a factor of 3 rather than going up by a factor of 3. So essentially, this one will now be at 2/3 there, and it'll be at 6 on this side. And so it's going to be doing the same story, just backwards. So that's what graph number 2 looks like. Now as for graph number 3, it is, like graph number 1, a case of exponential growth. The difference is that, that after 1 unit in time, it'll only go up by a factor of 1.5, which will only make it now equal to like 3. And if we go backwards in time, that'll be 2 divided by 1.5, which is going to be 1.3. So what that means is that here we're going to only be at 3 on that side, and we're only going to be at 1.3 on this side, so it's going to be slightly higher. And so what that means is, it's going to be a milder slope. So that's what the effect of these sorts of things will be. They all pass through the same point of 2, but the difference is that they what they do on the left and the right of it depends on the b. So that's the first case. Second case, what we're going to have is a collection of 3 exponential functions that share the same value of b and differ in their a. So let's say y equals 2 times, let's say 3 to the x. Actually, that's the same as the problem on the homework. So let me make a quick change. Quick change here. Y equals 4 times 2 to the x. Y equals, now let's say 2 times 2 to the x. And let's say y equals negative, not yet, make it 1/2 times 2 to the x. We'll deal with negatives and such when the time is right. So that'll be a 1, that'll be a 2, and that'll be a 3. Okay. So in all cases, the growth factor here is 2. But what is different from case to case is the y-intercept. So we're going to say that this is 2. This would then be 4. That would be 1. That'd be 3, and most importantly, that'll be 1/2. So then, as we track it, as it goes to the left and goes to the right, it goes up by a factor of 2 each step to the right. It goes down by a factor of 2 each step to the left. So what that means is, if we are taking one that starts at 4, 1 second later, it will have doubled to make 8, which if that's 4, let's say 8 is like right there. So that's going to be way up there now. And meanwhile, backwards 1 step in time, it will be only half of what it was. So that'll be going like that. So that's what graph number 1 will look like. It's growing from an already high value even higher. Meanwhile, graph number 2 is going to be going through this point. 1 second later, it'll be multiplying that point by 2, which will put it at 4. 1 second in the past, it'll be half of that, which will be at 1. And that'll put us there. And then the last one here is 1/2, which 1 second later will have gone from 1/2 to up to a value of 1, and 1 second before it'll only be at a quarter. So notice that these shapes here are in fact all the same, but what's happening is that it's just more or less stretching or compressing it by a factor of a. The takeaway of this is, so note, we can also think of a not just as being the initial value, but we can think of it as being a vertical stretch factor. As being vertical stretch or compression of the basic function f of x equals just b to the x. Thus, the a doesn't change the shape of the graph it just amplifies the y values. Now the b, however, does change the shape. The value of b does change the shape. Namely, it affects how sharp the bend is. It affects the sharpness of the bend. Now, an example of the kind of thing that we might have to do is match the following graphs to their formulas. And what this will look like is we'll have a little bouquet of functions, and they will each have, their graph will each tell us some specific information about their values of a and b. And let's say that first off we have a function that is exponentially growing, going up that way, and another function that is exponentially decaying, but through the same point on the y-axis, but make them more or less symmetrical, the two. And then let's say we alternatively also have the function growing gradually, like so, and a function that is growing more sharply. It can be a little hard to see the effects of the different b values when it's on the decaying side of things, but on the growing side you can see a little bit better. And then let's say we've got here the same picture in reverse, so it's got a relatively steep fall. And then we've got one that has a shallower decline. And we'll put all of our labels on the side that's pointing upward, because those are a lot easier to distinguish from each other. We'll say A, B, C, D, E, and F for the 6 functions. And now we'll line them up with some functions. We'll call the functions here one. Let's just say y equals. And now let's go with 3 times 1.5 to the x. Function number 2, let's say, is equal to y equals 3 times 0.67 to the x. 3, let's say, is equal to y equals 5 times 1.5 to the x. Function 4, let's say, is y is equal to 3 times 3 to the x. Function 5, let's say, is equal to y equals 5 times 0.67 to the x. And then finally, let's say that we have function number 6, which is y equals y equals 3 times 1/3 to the x. Alright, now when it comes to trying to figure out which of these graphs goes with which of these functions, we only have 2 pieces of information to work off of. We have the a and the b. And so based on that, we can figure out that d and f, they have a very similar shape. So they seem to have probably about the same b, but the difference is that one of them has a higher value of a. So d has a high a, and it has growth, which means b is bigger than 1. Which means that it must go with, out of all the choices here, that only could be function 3. Alright, as for E, that one has a low A, and it has fast growth. So that means a high B. So that means that So it's okay, this one is check. Alright, now so that leaves us a lower value of b, but a lower value of a but a higher value of b, which appears to be option 4. As for f, it's got the low a and slow growth. Which means the lower b, but still greater than 1. So lower a just means the 3 for in front, and the lower b, this one's also taken, means we're talking about graph or function 1. So d, e, and f would be 3, 4, and 1. And then for a, what we're talking about on that side looks to be the mirror image of f, which means that it is the low a and it is the slower decay. So that means b close to 1 but below. So out of the options that remain, we are still looking at the value of 3, but it has to be the milder growth. And if you look at the two options, there's 2 and there's 6. One of them has a b that's much smaller than the other one. This is like 0.33 instead of 0.67. So we're talking here about graph 2, and it's because it didn't drop as fast as b did. B, on the other hand, does drop fast. So low a, fast decay, which means b close to 0. Close to 0, which puts us then, so this one's already taken care of. So that means we are talking about number 2. Sorry, 2 is the one that was already taken care of. This is now the one that's taken care of, so we're talking about number 6. And then that leaves only one left to do. I'll put it up here. So C has the high A and the decay. So it would be less than 1. It's the only decaying one from the upper ones. So that means that we are going to be talking about, in the case of C, we're going to be talking about 5. So that's how you can match them. Now, in general, when you're looking to characterize the values of the b and the a of graphs, you just have to keep in mind this. So note, b close to 0. This means rapid decay. So b just below 1. This means slow decay. B just above 1. This means slow growth. And B above 1 means faster growth. and say b more above 1. In addition to the effect of A being thought of as a vertical stretch or compression, we can do all the other sorts of vertical and horizontal transformations that we know and love to exponential functions. Note, we can perform the usual transformations. To exponential functions. And the transformations that we're going to be looking at specifically here are going to be everything except for horizontal stretch or compression. Those ones are the most complicated ones. Those we'll deal with in a very specific context. So let's look at the transformation. Various transformations we can do. The graphical side of things, and then what changes. So first off, one transformation that we can do is we can do a vertical shift, up or down. And then graphically, what that means is that we are going to be maybe moving it up like that. Maybe it's going to be moving it down, something like that. So the changes here are going to be to the vertical shift. So we could have like 2 to the x plus 1, 2 to the x minus 1, for example. And then what changes here? Well, notice a couple things change. This is the first transformation, so we'll just call it 1. Vertical shift. And what changes is the y-intercept changes, and the range changes. Oh, and also the horizontal asymptote. Another change that we can make would be we can do a vertical reflection. And that's also called a reflection about the x-axis. So then that would be doing something like negative 2 to the x, or negative 1/2 to the x, things like that. And then from the graphical side of things, that's going to then produce graphs that are exponentially growing, but in a negative way. Or exponentially decaying, but in a negative way. And then what changes here? Well, we can see that also the y-intercept and the range will change. However, the horizontal asymptote will stay the same. And then the third major kind of transformations we can talk about are of the horizontal variety. And for horizontal ones, what we can do, so 3, we can talk about a horizontal shift. And then that would be something like 2 to the x plus 1, which means it went left 1. Or 2 to the x minus 1, which means it goes right 1. And then graphically, what this means is that now what we were using as our basis for our A is actually being shifted over. And in particular, the value that used to be the A is not the y-intercept anymore, but is now the shifted version of the y-intercept. So this changes again the y-intercept. But it doesn't actually change the range or the horizontal asymptote. And then the fourth thing that can be changed here would be a horizontal reflection. Which also is called a reflection about the y-axis. And that has the graphical effect of a negative x on the formula, or just like that, that's fine. And then what that's going to be doing is it's going to be taking the 2 to the x and running the tape backwards, which actually turns growth into decay and decay into growth. Growth becomes decay when you run the tape backwards, and decay becomes growth. So now let's try to actually do some of these changes to a relatively familiar style of function. So for example, let's take this. So sketch a graph of each of the following. And then give the horizontal asymptote, the domain, and the range. Alright, so first off, let's take as a graph f of x is equal to 3 to the negative x. So first off, the basic graph here is is y equals 3 to the x, which is just a nice regular exponential function with an a of 1, b of 3. So the basic way this should look is it should be equal to 1, and it should be equal to 3. It should be going like that. Anyway, so it should be doing exponential growth at a rapid clip. But now what's going to be happening is that it's going to be going through 1, but backwards. Because it had a horizontal reflection. Now, notice that the domain of this function as drawn is still what it was before. The range of this function as drawn is still what it was before. And the horizontal asymptote of this function also is still what it was before. The only difference is that it's approaching it on the right instead of on the left. But the horizontal asymptote is at y equals 0. The domain is still negative infinity to infinity, all real numbers. And the range, is still 0 to infinity. So it's still all the positive real numbers. Now let's try a different transformation of the same function though. So let's take example B. We'll do f of x equals 3 to the x plus 2. So the basic here is still 3 to the x, but now it's shifting it up 2. Which means that if the original, so if the original was y equals 3 to the x, which went like that, then this one is going to be doing that same thing all up 2 units higher than it used to be. So y equals 2, which means the y-intercept also got shifted up by 2 units. So now it's going like so. So we've got now a new horizontal asymptote. And that horizontal asymptote is at y equals 2 instead of at y equals 0. The domain is still negative infinity to infinity. None of the transformations that we're discussing in any of this will have any effect actually on the domain, but they will affect the range. So the range was previously everything above 0. Now it's everything above 2. So it's all reals greater than 2. And that's the way your book, by the way, describes these. It describes them based on the words, not the interval notation, but this is actually a good opportunity for using the interval notation, so I encourage you to do that. And then finally, the last one that we're going to look at is a horizontal shift. So f of x equals, now let's take 3 to the x minus 2. So what that means is it is a shift to the right 2 units. So the basic here is, as usual, y equals 3 to the x. 3 to the x. And this is going to the right 2 units. And so what that means is basically the point that used to be at 0, 1 is now going to be at 2, 1. Other than that though, there's no visible difference. So what this means is that the horizontal asymptote is actually still where it was. Horizontal asymptote at y equals 0. The domain is still what it was. It's negative infinity to infinity. And the range is still what it was, which is 0 to infinity. Now, notice that the effect of the horizontal reflection was visible on the graph, but not in our description of the horizontal asymptote, or the domain, or the range, or anything like that. But what would change under that would be the end behavior. So let's talk about that. End behavior of exponential functions. So essentially what happens on each of these is that the horizontal asymptote is only one-sided. In the case of growth, it's going to the left. In the case of decay, it's going to the right. Because the horizontal asymptote is one-sided, one direction will level off at a y value, and the other will go to either plus or minus infinity. And it's all going to be a result of whether it's growth, decay, and what kind of function transformations there are. Use a sketch of the graph to decide. For example, so describe the end behavior. And here, let's say the end behavior is something like this. F of x is equal to, let's say, negative 3 times 2 to the x plus 1. So now thinking about what's happening here, we have a horizontal asymptote being shifted up 1 unit. That's the effect of that. And we also have we have exponential growth. So this is the basic. Exponential growth is going like that. And this amplifies it, but this makes it go downward. So it's growing away from its horizontal asymptote in a downward direction. And if you wanted, you could actually figure out from these things what the actual y-intercept would be. It's not really important for us to know. The important thing for us to know is which way it's going. So here we have x going to negative infinity, y is going towards 1. Over here what we have is x going to positive infinity, y going to negative infinity. So we can now put that all together and we can say f of x approaches 1 as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. And let's see, let's try another one. Let's go with f of x equals 2 times 1/3 x, 1/3 to the x, minus 1. So now the basic is going to be 1/3 to the x, which is a classic case of exponential decay. But now, when we think about all the effects of the various pieces here, we've got a shift downward. So what used to be a horizontal asymptote at y equals 0 is now going to be at -1. And what we've got is an exponential decay going that way. So what this means is that as x goes to the left to negative infinity, y is going up to positive infinity. You can see by the upward arrow there. Here, x goes to positive infinity, y is going to -1. It's leveling off. So we can sum that all up by saying f of x goes to goes to positive infinity as x goes to negative infinity, and we can say f of x approaches -1, I mean, as x goes to positive infinity. And in the last of these, let's try something like f of x equals 2 times 3 to the negative x plus 1. So the basic here is y equals 3 to the x, which is classic exponential growth. However, the things that have happened to it are, for one thing, a shift up by 1 unit. The 2 stretches it, not that it really matters that much to us, but the important thing here is this negative reflects it, so it goes backwards. So that means we are talking about something going backwards, which makes it, in effect, decay. So then here, x is going to negative infinity, that's the left, y is going to infinity, x on this side is going to infinity, that's the rightwardness, and y is going to 1. So we can put that together and say f of x is going to infinity as x goes to negative infinity. And we can also say f of x is going to 1 as x is going to infinity. Now, the last task that we can undertake here is to use technology, which we haven't done yet, to solve some exponential equations. So here's the idea. So let's say that we had an exponential equation such as something like this. 3 equals negative 2 to the, negative 2 times, times 5 to the x plus 10, something like that. So if this is the equation that we're trying to solve, then what we can do is use some kind of graphing technology, such as Desmos, to graph y equals left-hand side, by which I mean left-hand side of the equation and right-hand side of the equation. And then you would look for where these two graphs intersect. Look for the x values of the points of intersection. These will be the solutions. So in our example, if we wanted to solve 3 equals negative 2 times 5 to the x plus 10, I would need to graph y equals 3 and y equals negative 2 times 5 to the x plus 10. And then I would be looking for the intersections that they would be producing. Now, it's not my business to try to draw this too accurately right now, because I can't use my hand-drawn rough graph to estimate any solutions. But what I can do is I can use Desmos to produce these solutions for me. So let's now switch over to that. Alright, I brought up our old friend Desmos, and now let's see what we would have to do to solve this equation. So we can put in y equals the left-hand side, which is 3, and y equals the right-hand side, which is negative 2 times x to the 5th. 5 to the x. X to the 5th would not be an exponential function at all, but a power function. And then plus 10. Now, depending on how the Desmos window was automatically set up, you might be able to see it or you might not be able to see it, but what we're looking for is the point of intersection of these two lines, so the red line and the blue line, which is right there. You just click near it, and Desmos will tell you what that point of intersection is. If necessary, you can zoom in, and if you zoom in far enough, it will give you more precision than it had before. Downside is you might lose your point, but there it goes. And so you can get more decimal places if you need them. So there is 0.7784. And what I just drew right here is what I saw on Desmos, which gave me the point right there, and what I'm interested in from that point is the x-coordinate, which will give me the solution. And I can see from the graph there aren't going to be any others, so this is the only solution to this equation. Alright, well that covers 6.2. Join me for the next episode of Math 111 on Wednesday. Till then, bye!